So today we will be discussing on spontaneity, entropy, and Gibbs free energy. Firstly, we'll talk about spontaneity. So this spontaneity means the potential, okay, to proceed without the assistance of any other external agency, okay. So without any other external agency, it will just proceed, okay. So a process, okay, this is a process. So this spontaneous process, it is irreversible process, okay. This process will go, okay, in one direction, okay, and sometimes it is it proceed in one direction. So it's sometimes this process proceed in unidirection, okay, we call it unidirection, and may only be reversed by some external agency, okay. So this process will proceed in one direction, okay, and if there is an external agency, okay, this process can be reversed, okay. Now let's take some example for better understanding. Suppose this is iron, okay. So if you heat this part, okay, this end side, okay, it will slowly travel from this direction to this direction, okay. So this is an example, okay, of flow of heat, okay, from one direction to another direction, okay. So there is a unidirectional, okay, that means one direction, okay, flow of heat from this side to this side, okay. So this is an example of spontaneous process, okay. So in nature, okay, those chemical processes, okay, occurring, okay, are spontaneous process, okay. That means they proceed in one direction, okay, or they are unidirectional, okay. So this spontaneous process, it is unidirectional, okay. So the change is unidirectional, okay. Suppose if we take hydrogen and oxygen, okay, and they are left, okay, at room temperature, okay. So let's say 4 years, okay. So there will be reaction occurring, okay, but it will be at a very slow rate, okay. So this is also an example of spontaneous process. Next one is decreases in enthalpy a criterion for spontaneity, okay. So when there is a change or decrease in enthalpy, okay, so is it a criterion for spontaneity? So this enthalpy, we are going to check whether it is a criterion for spontaneity. For this, let's see an exothermic reactions, okay. So we may think that this exothermic reaction may be spontaneous, okay. So it may move in one direction. Let's take the example of this one. Half N2 gas plus 3/2 H2 gas to give this ammonia. Yes. So enthalpy of reaction here is minus 46.1 kilojoule per mole. Let's see another one, okay. Formation of this HCl, half H2 gas plus half Cl gas to give HCl, so 1 mole of HCl. Now for this one, delta RH minus is, this is minus 92.32 kilojoule per mole. So in this case, what is happening is this reaction is exothermic, okay. That means heat is released, okay. So there is a decrease in enthalpy in this case, okay, means heat is released. Now let's see another example, endothermic reaction, okay. half N2 plus oxygen to give nitrogen dioxide. So for this case it is endo, okay, heat is absorbed. Next one is, let's see another one, graphite, okay, carbon, electrodes of carbon, solid react with 2 moles of sulfur, which is liquid, okay. This will give carbon disulfide. So enthalpy change here is 128.5 kilojoule per mole. So in this case, what is happening is, for this, okay, exothermic region, okay, even the process is exothermic, there is spontaneity, okay, and this one, even it is endo, it is spontaneous, okay. So the reaction proceed, okay. So even there is change in enthalpy or decrease in enthalpy, okay, increase or decrease in enthalpy, this spontaneity takes place, okay. So that means enthalpy is not a criterion for spontaneity, okay. So this, with this example, we come to the conclusion that enthalpy is not a, okay, or decrease in enthalpy is not a criterion for spontaneity. Next one. So we are going to come across a new term, okay. Before coming to this new term, let's see one example, okay. Say 2 gases, okay, separated by a chamber, okay. So these are chamber and separated by this wall, okay. So let's say this A S, this is B, okay. So we can clearly define this one as A, this one as B, okay. If we take one, or we can take this A, this B separately, okay. But what happens when we remove this wall, okay? When we remove this wall, this case A and B will combine, okay. When this A and B combines, okay, we cannot determine, okay, which one is A, which one is B, okay, because they will mix, okay. And if they mix, okay, there is disorder, okay, and we cannot predict, okay. So that means this system has become chaotic, okay. So for this case, we bring another term known as entropy, okay. So this entropy means randomness, okay. So this is the degree of randomness or disorderness of the system, okay, this entropy. So this entropy we denote it by S, okay, S, entropy, okay. So this entropy means randomness or disorderness, okay. So when there is randomness, means it simply means spontaneity is increasing, okay. Now this change in this entropy is denoted by delta S, okay, delta S, and it is given by Q by T, okay. So Q is related to heat, okay, so it will be Joule, and T unit will be Kelvin, okay, for temperature, so Joule per Kelvin, okay. So this will be the unit for entropy. Now for better understanding of the entropy, okay, let's discuss some examples, okay. So in a chemical reaction, okay, molecules, ions, okay, we can take those molecules, okay. So suppose A plus, let's say A A breaks into A1, A2. Okay, so it breaks into A1, A2. So that means there is increase. Okay, A breaks into A1 and A2. That means from 1 to it becomes 2 molecules. Okay, so randomness increases, that means entropy increases. Okay, this is one example. Okay, and we can take the example of gas also. Okay, so these gas molecules, they are free to move anywhere. Okay, they move here and there, and there is randomness. Okay, for gaseous. Okay, so for gaseous state, entropy will be the highest. Okay, and for crystalline solid. Okay, so this crystalline solid, they are most ordered. Okay, they are ordered. Okay, the structure are highly ordered. Okay, so in this case, since they are ordered, that means very less or very less randomness will be observed. Okay, that means entropy will be least. Okay, for crystalline solid. Okay, compared to this gaseous. Okay, now another thing, this entropy is a state function. Okay, so that means it does not depend on the path. Okay, it does not depend on the path. That means it is path independent. So a system, okay, at higher temperature, okay, if we applied higher temperature to a system, the randomness will increase. Okay, so at higher temperature, entropy increases. Okay, please note this one. Okay, now for this case, okay, according to this formula, delta S, okay, is inversely proportional to T. Okay, so this is in terms of change in entropy. Okay, this one is just entropy, this is change. Okay, for change in entropy, why it is not proportional to temperature? Okay, why it is not proportional to temperature, let's discuss here. Suppose they are two bigger. Okay, and we suppose this bigger is in the lab, this is outside. Okay, outside at higher temperature. Okay, let's say 40 degrees Celsius, and this one at 10 degrees Celsius. Okay, obviously this one will have higher randomness. Okay, so outside the temperature is higher. Okay, so entropy will be higher. Okay, randomness will be higher. For this one, the randomness will be lower since the temperature is at 10 degree. Okay, and this one at 40 degree. Now for this case, let's say we applied same heat. Okay, same amount of heat. Okay, to both. Okay, so this one, it's the randomness is already higher. Okay, so it will show less randomness. Okay, since this one it's in 10 degree and less randomness. Okay, if you apply the same heat, this will, okay, show much higher randomness. That means this delta S, okay, for this one will be higher. Okay, and this one, it was already in higher randomness. Okay, that means if we apply the same heat, okay, this one at higher temperature will show low value of this one, delta is change in entropy. Okay, we are talking about change in entropy. Okay, so this will have, at low temperature, this will have higher delta S. That means change in entropy. So that's how we got this one. Okay, delta is inversely proportional to temperature. So that it simply means that change in enthalpy when this change in entropy when it increases, then temperature should be lower, okay? And when temperature higher, this entropy value will be small, okay? Now this entropy, okay, this delta S for a system is given by, for a system it's given by delta S total, okay, total delta S system is delta S surrounding. Okay, so this is for the entropy change, okay, for a system, okay, and surrounding, okay. So delta S total will be this one, system and surrounding, okay. So this will be greater than 0, okay. Now at equilibrium, this delta S will be is equal to 0, okay. Now we know that this, for both reversible and irreversible process, this delta U is equal to 0, okay, for an isothermal condition, okay. This isothermal condition means when temperature is constant, okay, when T is equal to 0, okay. So internal energy will be 0. But for this irreversible process, okay, delta S, okay, total delta S system plus delta S surrounding is not equal to 0, okay. So this is not equal to 0 for irreversible, okay. Only for reversible it is 0, okay. So when irreversible we will see some randomness, okay. That is why it is not equal to 0. Next one is Gibbs free and spontaneity. So this, okay, entropy and this one enthalpy, okay, increase in entropy and enthalpy can alone, okay, cannot determine the spontaneous or spontaneity of change in the system, okay. So we cannot determine this, okay, with entropy and enthalpy change alone, okay, the spontaneity of a system, okay. So example, like for a closed system or open system, okay, there is change in enthalpy and entropy, okay. So because of that, okay, we come to a new term known as Gibbs energy. So what is this Gibbs energy, okay? So this Gibbs energy is a thermodynamic function, okay. This Gibbs energy is denoted by G, okay. So it is given as delta G is equal to delta H minus T delta S, okay. This is enthalpy, this temperature, this delta S means entropy, we all know that, okay. So this delta G, okay, means energy, okay, available to do useful work, okay. So why it means energy to do useful work means in this entropy we found out that it is Q by T, okay. So T cancel, what remains is this one, Q, heat, or let's say, okay, let's say energy, okay. So this delta H is also energy, okay. So that means this delta G, okay, is a net energy, okay, is a net energy and sometimes we call it as free energy of the reaction. Okay, so this is the free energy or net energy available. Okay, so there is a criterion for this delta G. Okay, for criteria or criterion, okay, for spontaneity at constant pressure and temperature. Okay, so the first condition, if delta G is negative. Okay, if delta G is negative, that means delta G is less than 0. Okay, so the process will be spontaneous. If delta G is positive, okay, that means it will be greater than 0. The value will be greater than 0. That means non-spontaneous. Okay, the process will be non-spontaneous. So through this delta G, okay, or change in Gibbs energy, we can determine whether a process is spontaneous or non-spontaneous. Okay, and if delta G is equal to 0, that means it's in equilibrium. Okay, equilibrium, or the process is equilibrium. Next is Gibbs energy and equilibrium. So let's consider A plus B, a reversible reaction. Okay, reversible reaction to give C plus D. Okay, so for a reversible reaction, we know that delta G is equal to 0. Okay, so for this one, Gibbs energy for this one, okay, let's consider the reactants and products, okay, to be in their standard state. Okay, for this one, for this equilibrium reaction. Okay, therefore since delta G is 0, okay, 0, and the equilibrium constant for this reaction will be Rg, okay, standard RT ln K. Okay, or we can write it as delta Rg standard minus RT ln K. Okay, so if you convert this into log, okay, it will be minus 2.303 RT log K. Okay, this is for equilibrium. Okay, so we can use this relation, okay, to calculate some problems, okay, in related to this equilibrium. Okay, now let's see another topic, entropy and second law of thermodynamics. So what does second law of thermodynamics says? So it says that entropy of an isolated system always increases. Okay, so for an isolated system, entropy will increase. Okay, so that spontaneous process we have discussed that. Okay, so in spontaneous process without an external process, okay, that process continues, okay, in unidirection. Okay, in this case, okay, let's take an example of a room. Okay, room. So if you leave the room, okay, for some days, okay, let's say weeks, okay, so the room will become untidy. Okay, so you untidy, okay, and you will find dirts around, okay. So when you come back, you have to clean the room. So you have to clean and tidy the room. Now, so when you leave that room for weeks, okay, that means entropy increases in that room, okay. That means randomness increases, okay. And when you come back, you have to clean it, okay. So when you clean it, entropy decreases, okay. So likewise, okay, entropy of a isolated system increases, okay. So this second law also explain, okay, why some exothermic, or why in that exothermic reactions, okay, this spontaneity is common, okay. So usually you will observe that in exothermic reactions, heat is released, okay. So this heat is released, okay, and taken up by the surrounding, okay. So the surroundings will take up this heat, okay, and then as a result of this, what will happen? Entropy will increase, okay. And if this entropy increases, that means spontaneity also increases, okay, or it will give rise to spontaneous process, okay. Now next one, absolute entropy and third law of thermodynamics. So this third law stated entropy of any pure crystalline substance approaches zero at the temperature approaches absolute zero. This is called the third law of thermodynamics. So now that we have discussed about the entropy, okay, for a crystal and for gas, right? So in crystal, it is in perfect order, okay. The molecules, okay, they are in perfect order, okay. That means there is no randomness, okay. But for gas, the molecules, they are moving here and there, okay. They are not at one position, okay. So there is randomness, okay. So for crystalline, at absolute zero, okay. So when this temperature approaches absolute zero, means the most possible, okay, or the lowest possible temperature, okay. At lowest possible temperature for a crystalline, the entropy will approach zero, okay. That means zero. So for this crystalline, entropy will approach zero, but for gas, entropy will be highest, okay. So this is the third law of thermodynamics,